So last time we were looking at what creates a magnetic field and a little bit of what a magnetic field does. We've got a moving charge, which we call the source object, creating a magnetic field. And then that magnetic field exerts a force on another moving charge, which we call the test object. So in a lot of ways, very similar to the general structure of an electric field, but the charges have to be in motion. And that could include currents. If you've got current flowing through a wire, that counts as a moving charge. And we can use some formulas to determine the amount of magnetic field or the amount of force. And we can use the right-hand rules to determine the direction. Generally, if you're talking about the source charge creating a magnetic field, you'd use the first type of right-hand rule. And it's not just the right-hand rule number one, it's an entire category of first type of right-hand rules. Whereas if you're looking at the magnetic field exerting a force on a moving charge, you can relate those directions using right-hand rule number two, or the second category of right-hand rule, I should say. But a couple of things you can do even before you invoke right-hand rules. For this interaction, the source charge creating a magnetic field, you know the magnetic field that it creates has to be perpendicular to the velocity or current, if you're talking about current flowing in a wire. And the magnetic field has to be perpendicular to the radius vector, like just the straight line vector from the source charge to the location of interest. The magnetic field at that location has to be perpendicular to that radius. Likewise, in this interaction, if we're talking about a magnetic field exerting a force on a moving test charge, the force that the charge experiences is going to be perpendicular to the magnetic field, and the force is going to be perpendicular to the velocity of that test object, or the current if we're talking about wire. I guess I should specify this as velocity of the source object versus velocity of the test object. Any questions on those directional things so far? And do you have any formulas yet describing how strong the magnetic field is going to be or how much force you're going to experience? Like for instance, if you just got a long straight wire with current flowing through it, do you have a formula for how much magnetic field that would create?
I think that was the mu naught times I divided by 2 pi over.
Yeah. If you're talking about the magnetic field from a wire, just a long straight wire, you can use magnitude of the magnetic field is mu naught, which is just the universal constant. It's essentially a unit conversion sort of thing for magnetic fields, times the current in the wire, divided by, was it 2 pi r?
Yeah.
Which means the faster the current is flowing, the stronger the magnetic field is. And the further you are from the wire, the weaker the magnetic field gets. So you can use that for calculating how strong the magnetic field is at any location near a wire. If you've got a wire with current flowing through it that's creating a magnetic field, this will tell you how strong the magnetic field is. Any questions on that so far?
Casey, I just had one question real quick. So whenever we're say solving for like a total magnetic field, do we find direction always first and then solve for the magnitudes individually of each one, if that makes sense?
If you've got a magnetic field caused by several sources, like if there's several wires of current, typically what you'd want to do, if you just choose a location, you want to look for what's the magnetic field caused by one of the wires at that location in terms of both magnitude and direction. And then what's the magnetic field caused by the other wire at that location. And then you can add those vectors together to get the actual magnetic field at that point.
Okay, thank you.
Mm-hmm. And you don't necessarily need to actually find the numerical X and Y components right away. You could look at it in terms of symmetry, see if there's anything that you can expect to cancel out. Like maybe the X components cancel out and you just need the Y component, or vice versa. So look for ways you can simplify things geometrically before you actually put in all the numbers. Any other questions on this so far? And what about the second situation? If you've got a magnetic field creating a force on a moving charge, do you have a formula for how much force you can expect? The direction you can get from the second right-hand rule. What about the amount of force?
Is it Q for the charge times velocity times the magnetic field and then sine theta?
Yeah, that should do it. And we should probably interpret this whole thing as being an absolute value because we're just looking for magnitude. We're not caring about direction yet because that's covered by the right-hand rule. But this just suggests that the more charge the particle has, the more force it experiences. The faster it's moving, the more force it experiences. Stronger magnetic field, of course, is going to mean a stronger magnetic force. And also the direction matters. And this theta here is specifically the angle between the magnetic field vector and the velocity vector. So what value of theta would lead to the force being largest? What value of theta would you plug in if you want sine of theta to be the largest possible?
90 degrees.
Yeah, 90 degrees. In other words, if the magnetic field and the velocity are perpendicular. If you've got a magnetic field in some direction and the particle's motion is in a perpendicular direction. In that case, if the magnetic field and velocity are perpendicular, you get the strongest possible force. When would this be weakest, though? What angle would make sine of whatever the smallest possible or the weakest possible?
0 and 180.
Yeah. If theta equals 0 degrees or 180 degrees, then we get no force at all. So if you've got a magnetic field, let's say magnetic field is straight up, and the particle is moving straight up or straight down, if the particle is moving along the magnetic field lines or directly against the magnetic field lines, the angle is 0 or 180. Sine of either of those is 0, which means no force at all. So you get the most force if the particle's motion is perpendicular to the magnetic field. You get no force if the particle's motion is along the magnetic field or directly against the magnetic field. And it doesn't have to be either one of those, of course. You could have, let's say, magnetic field. Let's say you've got a magnetic field straight up, and you've got a velocity vector that's on some diagonal. Would that lead to any magnetic force? Would there be any magnetic force at all there?
Yes.
Yeah, because they're not parallel, so you're not going to have no force. They're also not perpendicular, so you're not going to have as much force as possible. But whatever this angle is, there's your angle theta. sine theta is going to govern how much force you get. It's not going to be 0 because it's not 0 degrees. It's also not going to be 1 because it's not 90 degrees. It's going to be somewhere in between 0 and 1. So you're going to get some magnetic force, but not as much as you would if the velocity were perpendicular. If you actually use sine theta to split this up into components, though, you could split V into a parallel component and a perpendicular component. Which one of those components would be described by sine of that angle? The parallel component or the perpendicular component?
Perpendicular?
Yeah, the perpendicular component is opposite to theta, so that's what sine theta is talking about. So the V times sine theta just tells you V perpendicular. So you could also think of F as Q times V perpendicular times B. That way the sine theta is built into V perpendicular. So that's another way of writing force, just the perpendicular component of V times charge times magnetic field. Alternatively, you could keep velocity and split up the magnetic field into a perpendicular component and a parallel component. But I think it's usually easier to think of the velocity as being split up. Either way, you get some magnetic field or some magnetic force. If you multiply the magnetic field times just the perpendicular component of velocity, and then also times the charge, that tells you the magnetic force. And by the way, how would you tell the direction of the force in that case? If you got magnetic field upwards and velocity up and to the right, first of all, without even using the right-hand rule, what are the only possibilities for force there? If we know that force is perpendicular to magnetic field and perpendicular to the velocity. What would be perpendicular to upwards and up and to the right? Do you have any directions that are perpendicular to both of these?
Would it be into or out of the page, like in the z-axis?
In this case, the only possibility would be straight out of the board or straight into the board. Those would be the only options perpendicular to both of these vectors. And of course, that's just because the vectors are arranged in this particular way. If you instead had, like, let's say magnetic field outwards and velocity to the right, let's say, you could have magnetic force upwards or downwards, because that would be perpendicular to these two vectors. But the important thing is you're going to have a force that's perpendicular to both the velocity vector and the magnetic field vector. So once we've narrowed it down to two directions, in this case, outwards or inwards, how do you choose one of those two directions? If we know it's either outwards or inwards in this case, how do we decide which one of those?
We use the second right-hand rule.
Yeah, the second right-hand rule describes the relationship between a magnetic field and the force it exerts on a moving charge. So if the charge is moving this way, you typically use, if you use the three-finger variation. So if you hold your hand like this, thumb for velocity, index finger for magnetic field, and middle finger for force. Put your thumb in the direction of velocity, the motion of the particle. And note I can still swivel my hand around like this and still have my thumb pointing along the velocity. I want to point my index finger in the direction of the magnetic field. And you've got some flexibility there, because really it's the perpendicular component of velocity, magnetic field, and then my middle finger is now pointing outwards. So that suggests an outwards force here. That is, as this particle is moving up and to the right, it experiences an outward force, meaning it's going to go on a curved path. And this is usually what happens. Since the force is perpendicular to the test particle's velocity, that means the particle is going to curve its path because you have a force perpendicular to its own velocity. So charged particles moving in magnetic fields tend to follow these curved paths, which usually make it go in a circular path or sometimes a spiral path. But the particles tend to move in these sort of orbit-like shapes.
Casey, I have a quick question. So if we're trying to find the direction of the magnetic field, I know we use the right-hand rule number 1, but are we looking at velocity going perpendicular or to like towards the right side?
Do you mean like the magnetic field created by a source charge or source current?
Yeah.
In that case, you would use right-hand rule number 1. Yeah.
Okay.
So the V source here is the direction the source charge is moving, or the direction the current is flowing, if you're talking about a magnetic field caused by current in a wire.
Okay, so would we use like the V, like if it was going up like northwest, I guess, like how you drew it in the picture, would we point it towards that direction or like towards the perpendicular V
Well, in
direction?
this case, this isn't a charge. We're not looking at the moving charge creating a magnetic field. We're looking for the moving charge as the test object experiencing a force from the magnetic field. So that would be using the second right-hand rule.
Okay, thank you.
If we wanted to know the magnetic field this moving charge creates, you'd use the first right-hand rule. But in this case, we're looking at it as what's the force acting on this particle because of the magnetic field. One other thing on this, we've been assuming that this is a positive charge, even though we haven't really been talking about which type of charge, but this is if it's a positive charge. If it's a negative charge, what's going to be different? What do you think would happen to the force if we were talking about a negatively charged particle instead of a positively charged particle?
We would flip the direction.
Yeah, exactly. You just get an opposite direction. It flips over. So one way you can handle that, if you're dealing with a negatively charged particle, you could use the right-hand rule as normal, velocity, magnetic field, force. But then because it's a negative charge, the force is in the opposite direction. So that would be an inwards force instead of an outwards force. Another way you could deal with this is if you're dealing with a negative charge, if you know in advance that the charge is negative, you can just treat it as a positive charge moving in the opposite direction. Like if you have a negative charge moving to the northeast, just pretend it's a positive charge moving to the southwest. Velocity, magnetic field, force. So that would still be an inwards force. Or a third way you could do that for negative charges, just use your left hand instead. Velocity, magnetic field, force. Either way, we get an inwards force on that negatively charged particle. Could you explain one more time why it goes in a curved path? Yeah, if you're taking a look at a chart at any particle that's experiencing a force perpendicular to the velocity, this is really the key here, that the force is perpendicular to the velocity. Let's say you have a particle that's moving, let's say, to the east. But it's experiencing a force perpendicular to that. Let's say a force to the north. If you had a force in the same direction as velocity, like let's say you had velocity and force. If the force was in the same direction as the velocity, what would happen to the object's motion? Like if an object is moving this way and you push it in the direction it's already moving, what's going to happen?
Would it increase its velocity?
Yeah, that's just going to make it go faster. Faster and faster and faster if you're pushing it in the direction it's already moving. What if they're in exact opposite directions? If you got an object moving this way, but you push it the opposite direction, what's going to happen?
It will slow down.
Right, slows down, maybe even comes to a stop and turns around. But note that it's still going to be parallel. It's not changing it's not really curving its path. But if you have a force that's perpendicular to the velocity, perpendicular is neither in the same direction nor in the opposite direction. It's exactly halfway in between. So this force, a perpendicular force, is not going to change the speed at all. But what does it change?
It changes direction.
Right, it's going to change the direction of the velocity. This particle is going to travel on a curved path instead of a straight line, because with no force, it's just going to move in a straight line forever with the same speed. But a perpendicular force causes it to change its direction of travel So a little bit later, its new velocity will be to the right and a little bit, or to the east and a little bit north. If we were dealing with a constant force, the force would still be straight up, so this would just keep getting steeper and steeper. But if we're dealing with the magnetic force is always perpendicular to the velocity of the test particle. So we're now going to have a force that's still perpendicular to the velocity. So this particle is still going to just curve its path. It's not going to change speed. It's only going to change which direction it's traveling. And if all it's doing is changing its direction, it's going to move eventually in this circular path. Or if it also has, let's say, a z component, it's going to move in a sort of a helical path, spiraling around the z-axis. So that's the sort of motion we usually get if we're dealing with a charged particle moving in a magnetic field. It tends to fall into either circular paths or helical paths. Any other questions on that so far?
I have a question.
Mm-hmm.
So I don't really understand how this is a circular path. It kind of looks just like straight to me.
This path? It's, well, it was moving in a straight line if there was no force. If there is a force, it changes direction. And then since the force is still perpendicular, it's going to change direction again, and again, and again, and again. So it keeps moving in a path that curves. And since it's curving in the direction of the force acting on it, that's going to form a circular path if it's allowed to continue. Because it's curving at this constant rate every so far where it goes forward. In fact, the magnetic force, yeah, go ahead.
Was it actually moving in the circular path, or was it just like those tangent lines? I mean, sorry, was it actually moving in the straight path, or aren't those straight paths just like the tangent lines that we draw on there, but it doesn't actually go in that direction? It actually goes in a circle?
Yeah, the velocity vector, I mean, vectors are always drawn as straight arrows, but the motion itself can be a circular path. It's just that on any point on the circle, the velocity is a tangent arrow to that circle. If you've got an object that's moving on a circular path, at any given instant, like let's say the object is right here at this instant in time, at that instant, the velocity vector is just a straight arrow tangent to the circle. That doesn't mean it's moving in a straight line. It's moving in a curved path. It's just that at this instant, this is the direction of travel. And then a little bit later, the direction of travel is now this way. Presumably same speed, just a new direction because its path has curved. Also, in order to keep moving on a circle, if there was no force at all, it's just going to go in a straight line. In order to move on a circular path, it's going to need force in which direction? What?
Is it like up?
What do you mean by up? Like at this point, if you apply an upwards force, you're going to make the particle go faster in a straight line. But we don't want it to go faster or slower. We don't want it to go in a straight line either. We just want it to go in a circular path at a constant speed. So if you want something to move in a circular path, what direction do you always need to apply a force on it?
Is it towards the radius?
Yeah, a radial force, specifically towards the center along the radius. In other words, a centripetal force. If you've got a force pointing towards the center, centripetal literally just meaning towards the center. Centripetal force means a force towards the center, and the only way an object can move in a circular path is if the total force is towards the center. If the total force is, let's say, towards the center and a little bit forward, it's going to go in a circular path but get faster. Towards the center and a little bit backwards, it's going to move in a circular path but get slower. But you've got to have a force towards the center of the circle in order to move on a circular path. So that's what the magnetic field is doing here. If you've got an object moving in some direction, but it's experiencing a magnetic force perpendicular to its direction of motion, then that magnetic force is acting as a centripetal force, and it's going to make this object move in a circular path by curving its velocity or changing the direction of its velocity vector. Any other questions on that so far? All right, let's try out an example then. Let's say we have two wires. Two wires that are both, let's say, both vertical. Actually, let's say one of the wires is horizontal. And these wires don't actually meet here. One of them just jumps over the other. So no contact between the wires, they're just crossing over each other. And let's say we have equal amounts of current flowing in both of them. And let's label these wire number 1 and wire number 2. And we want to figure out what these wires are doing to each other. For instance, let's say we want to know what's the force on wire number 2. Magnetic force on wire number 2. If we're trying to find the force on wire number 2, are we treating wire number 2 as the test object or the source object? If we want to know the force acting on wire number 2.
If the force is acting on wire 2, is that the test?
Yeah. So we're going to treat wire number 2, temporarily at least, as the test object, the test current. And we're going to treat wire number 1 as the source current. So the way we're going to visualize this, and of course what's really happening is just these two wires are exerting forces on each other. But we can visualize this as wire 1 creates a magnetic field. That magnetic field exerts a force on wire 2. So to figure out the magnetic field involved here, treating wire 1 as the source current, so we're ignoring wire 2 entirely for now. We're saying wire 1 creates a magnetic field. And how would we figure out which direction that magnetic field is?
We would use the first right-hand rule.
Yeah, first right-hand rule. And there's several variations on it. One of them we can use that would probably be most convenient. If you just point your thumb in the direction current is flowing, the curl of your fingers tells you the direction of the magnetic field everywhere around that wire. So over here, we're going to have outwards magnetic field. In front, we're going to have magnetic field to the right. And then over here, we get magnetic field inwards. The important thing really is the magnetic field near the test object. So looking at near the test object, we've got outwards and then inwards. And then of course, getting weaker as you get further away from the source wire. So we'd expect the magnetic field caused by wire 1 to be in this general arrangement, outwards and then inwards. You could also check each location individually using another variant of the first right-hand rule. If you, for instance, let's say you want to find the magnetic field here. You could put your hand at this location, stretch out your fingers straight towards the source wire, and curl your fingers in the direction current's flowing. Then your thumb tells you the direction of the magnetic field at that location. So at this location, hand stretched out towards the source, curl in the direction of current, thumb tells you inwards magnetic field. So over here, the magnetic field is into the board. Over here, the magnetic field is out of the board. And that just overall forms loops around the source wire. Any questions on that so far? And if we wanted to know how strong it actually is, we could use the usual magnitude of magnetic field equals mu naught times the source current divided by 2 pi r. So if you know the current and you know how far away a certain location is, you can calculate the strength of the magnetic field. Any questions on that so far? So now if we want to know direction of the force on wire number 2, we covered source current creating a magnetic field. Now we're going to look at the magnetic field exerting a force on the test current, wire number 2, because that current in wire number 2 does count as moving charge. So that moving charge, the current in wire number 2, how would we figure out the direction of that force on the current, the force on wire number 2?
The second right-hand rule?
Yeah, this interaction, magnetic field exerting a force, we would use the second right-hand rule. And probably the 3-finger variant is going to be most convenient there. You put your thumb, actually before we even do the right-hand rule, I would recommend checking just for perpendicularity. The fact that the magnetic force has to be perpendicular to the magnetic field. Force is always going to be perpendicular to the magnetic field. And force is going to be perpendicular to the velocity of the test object. Or in this case, the current in the test wire. So looking at those directions, you've got current is to the right, magnetic field is inwards. What would be perpendicular to inwards and to the right? What are the only possible directions perpendicular to both of those?
Up and down?
Yeah, the magnetic force here has to be upwards or downwards. Those are the only options perpendicular to both that magnetic field and that current. So we know the current over here is either upwards or downward, or sorry, the force is either upwards or downwards. Now that we narrowed it down to 2 possibilities, the whole point of the right-hand rule is to choose one of those 2. So if you use the usual 3-finger variant, thumb in the direction of velocity or current, the motion of the charge, so that's to the right. Index finger in the direction of the magnetic field, which is into the board here. So motion, magnetic field, force is going to be straight up. So we have an upwards force here. And if you can't find the flexibility to hold your fingers perpendicular to each other, or if that's uncomfortable, another way you can do this, direction of velocity, yeah, the V here is, the thumb here is representing the motion of charge. So that's the velocity vector of a test object, a charged object. Or since current is just the flow of charge, you just point your thumb in the direction of current. That's the motion of charge that we're talking about. So velocity or current, magnetic field, and force. And as I was saying, another way you could do this without trying to bend your fingers in weird ways, you could point your thumb in the direction of current, point all your fingers straight in the direction of the magnetic field, and imagine a push coming out of your hand. Like even if you just visualize pushing on the wire with the palm of your hand, that push is the direction of the force. So either way, this is going to be an upwards force. Which means not just this location, but this entire region of wire experiences upward forces. And where would those forces be strongest?
Closest to the source current?
Yeah, close to the source current, we've got a stronger magnetic field, so a stronger force. And then that force is going to get weaker because the magnetic field gets weaker. What about on the other side though? Over here, we've got an outwards magnetic field. So if you have velocity velocity is still to the right. We've got current to the right, magnetic field outwards. So force is going to be in which direction over here? If you got velocity, yeah, current to the right, magnetic field outwards. So the force is
down?
Yeah, we're going to get a downwards force. If you imagine, again, the force coming from the palm of your hand, pushing down on the wire. So near wire 1, we get a strong downwards force. And then that gets weaker and weaker as you get further away because the magnetic field gets weaker. So if you add up all these forces, what would you expect all these forces to add up to?
0.
Yeah, these forces are going to add up to 0, which means wire number 2 overall is not going to accelerate. But just because the forces add up to 0, what else isn't going to add up to 0 here? As forces, they cancel out, but any off-center force also counts as what?
Torque.
It counts as torque, yeah. These forces act as torque, and if we treat these, like let's say these are connected by a hinge, an axle in the middle, so we'll treat the middle as the pivot point. These forces create torque in the outwards direction. These forces create torque also in the outwards direction. So as torques, they combine. Like if you just start holding this and you push up on one side and down on the other side, those are all combining to try and make it rotate this way. So overall, this gets a torque trying to make it rotate towards this direction. So overall, if you've got these perpendicular wires, the overall force is going to be 0. They don't make each other accelerate, but they are going to make each other rotate. So wire 1 influences wire 2 by trying to make it rotate to align with wire 1. And this also works in both directions. If you instead treat wire 2 as the source, find the magnetic field it creates, and then find the forces on wire 1 is going to experience a torque causing it rotate the other way, aligning towards wire 2. So these two wires, as current flows through them, if the wires are free to rotate, they're going to swivel towards each other. Any questions on that so far?
Casey, I just have a question about the velocity being the same direction as current. So it's the test, like current you're saying is the same direction as velocity, not the source?
Well, velocity and current are kind of the same idea here. They're both just describing the motion of charge.
Mm-hmm.
When we say current is flowing this way, we're saying you can treat this wire as having positive charge moving in this direction. So in the second right-hand rule, thumb isn't just velocity. Thumb is the direction that charge is moving. And sometimes we call that velocity, sometimes we call that current, but it's all talking about the direction charge is moving.
Okay, that makes sense. And because that's the, we're focusing on the force on that current, that's why we're using that velocity. Okay, that makes more sense. Thank you.
And of course, current and velocity are measuring different things. Current is basically amount of charge that passes by per second. Velocity is how far the particles travel per second. But they're still going to be the same direction. It's just the direction that charge is flowing. Any other questions on that so far? One other useful bit of equation here, a bit of algebra, if we go back to the formula we were using for force on a moving test charge object, this is the force on a charged particle. You can't really apply this to the wire with current though, because this wire doesn't have a charge. Its overall charge is neutral. And it doesn't have a velocity, it's not moving. But we can still manipulate this equation to make something that will work. Specifically, if you look at velocity, how do we define velocity in the first place? What is velocity?
Meters per second, like the distance it travels per second?
Yeah, distance divided by time. So meters per second would be the units of measurement. Meters is just measuring a distance traveled, change in position. And seconds is measuring an amount of time, how much time it takes. So we could write this as Q times distance over time times magnetic field times sine theta. But if we rearrange the terms a little bit, specifically if we combine the charge divided by time, what do we call charge divided by time? That is how much charge per second, how many coulombs of charge per second. What does that mean, or what do we call that?
That current?
Yeah, this is the definition of current. If I'm telling you how much charge flows past this point in the wire per second, I'm telling you the current in the wire. So charge over time is current times a distance times magnetic field times sine theta. And for a wire, the only distance that really matters is the length of the wire. So we could write this as just L, length of the wire. So this is another formula we can use for force, specifically the force on a wire. If you want to know how strong the force on a wire is, a wire with current in the presence of a magnetic field, you can just multiply the current times the length of the wire times the magnetic field strength. And then theta is going to be the angle between the magnetic field and the alignment of the wire itself. So essentially equivalent formula, but written in terms of values that make sense for a wire instead of values that make sense for a charged moving particle. Any questions on that so far?
Wait, so the L is the length of the wire?
Yeah.
Okay.
If you've got a wire of known length, you can just plug in that length in meters times the current in amps times the magnetic field in Teslas times sine of the angle between them if they're not perpendicular. And that tells you the total amount of force on that wire. Or if you've got a very long wire, you can look at just a section of it at a time. Like maybe if you just plug in 1 meter for L, this will tell you the force per meter. And that's often more practical. We usually don't care so much about the total force on the entire wire. If we've got a long wire, we might split it into small segments and look at like, what's the force on this centimeter? What's the force on this centimeter? Force on this centimeter. So the force per centimeter, I guess you could even treat that as a force density instead of total force on the entire object. Any other questions on that so far? All right, while we've got time for it, let's take a quick introduction to magnetic flux as well. Because this is going to be important for the idea of magnetic induction, where you use a magnetic field to create current in a wire. Essentially the entire premise of generators and most power plants. The idea is if you've got a loop of wire and you've got a magnetic field, like let's say magnetic field is just pointing straight up everywhere. If you have some loop of wire, like let's say we just draw out this loop. The idea of flux is the extent to which the magnetic field vectors are going through the loop. So if you've got just some loop of wire and you've got magnetic field arrows going through that loop, that counts as flux. In this case, if we've got magnetic field going this way and we've got a loop of wire like this, does this vector go through the loop? If you just got this loop, so a loop like this, and you've got a magnetic field straight up, would you say that vector is passing through the loop?
No.
No, it's skimming along the surface, but it's not really going through it. To go through it, you'd have to be going on some direction, like let's say going inwards towards the loop or outwards from the loop. So something like this. In this case, if the magnetic field is parallel to the surface of the loop, it's not actually going through the interior of the loop. So we would say there's no flux at all. So in this case, if you've got something like this, this would be no flux. We usually write flux as a capital phi. We just say flux is 0 in this case. If you want to have flux here, one way to do that would be to, let's say, rotate the loop. Let's say we take this loop and rotate it so it's more of a horizontal plane. So something like this. If you could imagine that three-dimensionally. So you've got this loop that's been rotated so it's like this. And with this loop, the upwards magnetic field is now passing through the interior of it. So in this case, this would be a large amount of flux. So this is the flux here would be a large amount because the magnetic field lines are passing through the interior of the loop. And you can calculate this based on the usual way it's defined. Flux is defined as, essentially it's if you count up the number of magnetic field lines passing through the loop. So that's going to be stronger magnetic field means the field lines are more packed together. A larger area enclosed by the loop is going to mean it's enclosing more field lines. And also angle matters. So like for instance, if you rotate the loop, same loop but rotated means a different amount of flux. And we specifically use cosine of a certain angle. But the way we define this angle is based on the angle between the normal line. Same idea as the normal line we were looking at for refraction and reflection. So if you take the surface created by the loop, like if you imagine taking this loop, dipping it in bubble soap, you've now got a surface. The normal line we're talking about is a vector perpendicular to that surface. So there's our normal vector. The size of it doesn't really matter. We just need to establish a direction. Theta is the angle between the normal vector and the magnetic field. So in this case, since the normal vector and the magnetic field are in the same direction, theta would be 0. In this case, the normal vector would be straight out of the board. So the angle between this normal vector and this magnetic field would be 90. Cosine of 90 is 0, so no flux. But that's the angle we're talking about, angle between the normal vector to the surface and the magnetic field vector. Any questions on that definition so far?
I have a question. Other than like the mathematical way, like how do we know that there's no flux on the other one?
For this one, geometrically, you could say that the field lines, if the field lines are skimming along the surface, but not actually going through, there's no flux, because flux is supposed to mean to what extent the field lines are passing through the interior of the surface, or the interior of the loop. Oh, and that A is area within the loop. So the area enclosed within the loop multiplied by the magnetic field strength multiplied by cosine of the angle between normal vector and magnetic field. That will be largest when the normal vector is parallel to the magnetic field because the magnetic field is passing through the interior of the loop. This is going to be 0 if the normal vector, like in this case, normal vector would be, let's say, straight out of the board. So normal vector, perpendicular to the surface, and magnetic field, those are perpendicular to each other, so you get 0 as cosine of 90. That means no flux, conceptually, because these field lines are not going through the loop, they're just skimming along the surface. Any other questions on that so far?
So just to clarify, the picture you drew up on the top one, that's when it has the largest flux, right? Because the N and the magnetic field are both parallel. But if the normal line and the magnetic field are 90 degrees, then that's when it has the lowest flux, right?
In fact, it would have 0 flux because the field lines here are not passing through it at all. They're just skimming along the edge.
Okay, why can't you make the N like to the right, if that makes sense, to make it perpendicular?
The normal vector is defined as perpendicular to the surface itself. So whatever loop of wire you've got, It encloses a surface inside the loop. The normal vector is perpendicular to that surface. So in this context, if you've got just this loop of wire, you do have the option of normal vector straight out or normal vector straight in, but those would both be perpendicular to an upwards magnetic field.
Okay.
In this case, you'd have the option of normal vector straight up or normal vector straight down if you've got a horizontal loop. If you have the choice, though, it usually makes the most sense if you choose the normal vector that's already in the same direction as the magnetic field or closest to it. If you choose the normal vector off the magnetic field, mathematically it still works out. You get a bunch of extra negatives that end up canceling out but make it more confusing. So if you got the option, choose the normal vector that most closely agrees with the existing magnetic field.
Okay, that closely agrees with the magnetic field. Okay, thank you.
That will at least ensure that the flux is a positive value. Again, it doesn't really influence the end result, but it makes it easier to understand what's going on. All right, feel free to email me if you have any more questions about this, and we'll look into some examples of how to actually use this for induced current next time. See you later.